just to mention that on Monday, 10:30 a.m., there's a town hall meeting. And also faculty and students of Berkeley are welcome to attend. Now we continue with Tony, second hour. Tony.
Hi.
A question?
Hi, Tony. I have a question about your previous part. You said something about crypto hardness implies non-automatizability. I can't say that word, sorry. Are there results on the other direction? Like if a proof system is not automizable, you can get a one-way function from it or anything like that?
Not that I know of. Does anybody else know anything I don't know about forgetting?
Can you build one-way function?
It's completely open. Yeah. I don't think it's on an average case, but you can consider an average case version. Right.
Sorry, I didn't hear what whoever answered.
That's a good point. I meant assuming some average case version. That's true. You have to be an average case hardness. Oh.
Yeah, I think it's really, great question. Does anybody else have any?
I said if you have like an average case version of automatability where you have some sample distribution of instances and trying to automate on that.
Then you can try, but you don't know the results of that. Or you're saying the result is true.
I think something like that might follow for some artificial proof systems, but maybe not for natural ones.
No, I wanted the general for every proof system if it's not automizable in some randomized way.
You don't.
Because for learning, we have results like if there exists any class that's hard to learn, you can build a one-way function out of it, right?
Good
There's
point.
the FKL paper.
That's a good point, yeah.
Thanks.
Yes, well, the connection between proof systems and circuits is not that lucid. So I don't think there will be like something like this specifically. Yeah. Yes, Tony.
Any other questions? Okay, so in that case, I'll continue. And the next topic is lower bounds and conjectured hard to prove tautologies. I'm not going to talk too much about lower bounds we already have, more about the struggle to prove lower bounds for strong proof systems. And that's actually pretty related to metamathematics of complexity of lower bounds. So yeah, these two last topics will fit in nicely together. Okay, so just to survey what we know so far, the green line and down is the proof systems where we have exponential lower bounds. And the two, aside from AC0 Frege, which has its own story that I'll skip today, the rest of the proof systems under the line, all of the lower bounds can be proven using feasible interpolation. And there's also another method that's useful for resolution. It was the first lower bound that was proven for resolution, kind of used method one. It was by Armin Haken in 85. So even resolution bounds were open until 85. I know that seems a long time ago, but actually the question about resolution proof length was raised in the early 60s. So it was open for a long time, even for resolution. And so the first method is quite combinatorial. You first show there's various ways to do it, that you reduce the size question of a proof, like a resolution proof, to a question of width. So in other words, you show that if you can prove that any resolution refutation of some formula has to have at least one wide clause, meaning, a clause with like linear many literals in it, then you show that that implies that that any resolution refutation also has to have exponential size. And so once you have that reduction to width, then the lower bound on width is an expansion argument. So you take particular families of formulas that are kind of highly expanding in the sense of, if you look at the clause variable graph, it's highly expanding. And that sort of gives you that sort of look, if you look locally at the proof, which proofs that are rule-based like resolution tend to just are able to just form their information locally, that locally things will look very different than they look globally. And that's sort of the intuition for why the lower bound holds. But feasible interpolation is really, I would say, a more general method that has been used to prove pretty much all the lower bounds. It can give us all of the exponential bounds below the green line, except for, we'll leave AC0. I'm not going to talk about AC0 for now. I will say one thing that before we talk more. So there's, for IPS, that's the ideal proof system. There's actually a really exciting line of work. I think I got most of them referenced here, that introduce very, very lovely ideas and sometimes often build on known algebraic circuit lower bound techniques that have been able to establish a variety of really nice lower bounds. But the reason I'm not covering them here is that almost all of them, or at least the strong ones, are for systems of unsatisfiable polynomial equations that if you tried to convert them to, that they don't really convert to CNF. So the lower bound is not giving too much content or not saying much about the ability of the proof system to refute unsat CNF formulas. So the formulas themselves are not when you try to convert them to a CNF formula, they kind of become trivial. So that's why I'm not going to mention these, although it's a really, really nice, yeah. It would be nice to have a survey on all of this stuff at some point. Okay, so back to where we are here. Now, again, we said that there's sort of this dichotomy where we have the simple ones where we kind of have feasible interpolation, and then we have like the non-simple ones, which are above the green line, where we know that we don't have standard feasible interpolation under crypto assumptions. And so we kind of are stuck anytime we don't have feasible interpolation. And the simplest proof system. Yes.
So with the simple ones, isn't it the case that in some cases is a degree bound rather than a size bound? Oh.
Yeah, I think for all of them, there is also size bounds. Are you thinking of SOS, or like you can usually go from degree to size for these weak systems? Yeah, so SOS has a degree size trade-off just like resolution, so does polycalcium. Yeah, it does also.
No, it does not.
Well, it depends what you mean by degree size. If I'm just trying to, you don't need to get a great relationship, but if you have a proof of small size, you can usually hit it with a restriction, or you can even apply a general trade-off. So if you know that the degree is linear for null sets, assuming, yeah, I'm not sure why whoever said that, I'm not sure why you're saying that. There is a degree size trade-off for these. That's good enough to get exponential.
Well, maybe we can take it off point.
Yeah, but for all these proof system below the green line, there is a size lower bound.
Yes. There's an issue with SOS, but let's not get into that. It has to do with whether you're measuring size by coefficient size or monomial size. And it's known that there's an issue there because it does seem that there's results that show that sometimes you can't, the coefficient sometimes, cutting planes is another system, but we know that the coefficients never get big, but for SOS, they can grow exponentially big. So there is an issue about whether we really have SOS size bonds, but we do actually have SOS size bonds for some formulas. We just don't, we have to pay attention to the coefficient size.
Okay.
Okay, we have a lot of experts in here, but my basic point was a simple one, which is just for the ones below the line where we mostly have feasible interpolation, we are able to prove strong lower bounds. And I'll just mention that there's the feasible interpolation as Krajcik defined it has been generalized so that and Suzanne will talk a lot more about this, but now we can extract content, not just from interpolant formulas, the split type of formulas, but if you have an arbitrary CNF, there's a way to talk about computational content and the proof of an arbitrary one. And that's been very successful and has given us much stronger ways to connect circuit lower bounds to proof complexity bounds via lifting, and that stronger notion of interpolation for the stuff below the green line. And I think Susanna will talk about some of that. But I want to talk about above the green line. So I want to talk about strong proof systems, and I'm going to mostly I'll just think of Frege systems and extended Frege, but most of what I say is also true for AC0 with mod P, AC0 P Frege. Okay, so the first question is, I'm asking about conditional lower bounds. Can we prove lower bounds for, say, Frege systems modulo some circuit lower bound? And we saw for weak systems defined to be the ones that have feasible interpolation, we can do this. So we can usually show that from monotone circuit bounds, we get unconditional lower bounds for the proof system, and non-monotone circuit bounds will give us, non-monotone feasible interpolation will give us conditional lower bounds for the proof system, assuming the circuit bound. So we have this nice, really nice connection to circuit lower bounds when we have a weak proof system. And the question is, what about strong proof systems? We know they don't have feasible interpolation under crypto assumptions, but is there a different notion of feasible interpolation or a different way to extract computational content from a small Frege proof? And this is open. I will say that, unfortunately, because there's not enough time, there's a huge body of beautiful work about extracting computational content from feasible uniform proofs, so proofs in bounded arithmetic. And bounded arithmetic is like the uniform proof systems that correspond to these circuit, propositional proof systems. And there's very nice, lovely witnessing theorems, beginning with the work of Bust's thesis from '85, that shows that statements of a certain type, the type for all x there exists a y, a of xy, that statements of that type, if they're proved feasibly, that you can extract from them, a function for finding the y, and that function is in the corresponding TFNP class, depending on what the proof system is. So this is just a forward pointer that for uniform systems, we do have a very rich body of work connecting TFNP classes to proofs of certain types of statements. But for the propositional proof systems, we don't have anything like that. And it's not just because it's uniform versus not, it's really more has to do with the fact that the systems of bounded arithmetic are more expressible. They can express things that you can't express propositionally. So I'll just say one result that we have in the other direction. So the main thing that we proved about IPS was that superpolynomial lower bounds for IPS imply algebraic circuit bounds. They imply VP doesn't equal VNP. And this is not actually very hard to prove once you formulate IPS in the way that I said, and really just because, first of all, any unset CNF has sort of a VNP IPS certificate, has a VNP proof. But on the other hand, if you show that IPS can't prove a particular family of unset formulas, you're showing that no, because an IPS proof is just an algebraic circuit of poly size, you're showing that no algebraic circuit of poly size, that there is no, there is no VP algebraic, there is no algebraic circuit for it.
So this is for CNFs specifically.
Yes. Yeah. So we have this for IPS. IPS, as I said before, we don't know that it's a Cook-Reckhout proof system. And we also don't really know how strong it is, in the sense that even if you're happy to consider like Zermelo-Franco set theory or some very strong system, we don't know any kind of nice axiomatizable system can simulate IPS. So it does give a connection, a nice connection between a natural proof system and implying a really important circuit lower bound. But it's not saying anything about the standard Frege style systems. And that's open, whether or not we can show that superpolynomial lower bounds, extended Frege bounds imply some circuit lower bound, say, such as, P/poly not equal NP or some other non-trivial circuit bound. So what about unconditional Frege lower bounds? So one of the things that's very different about proof complexity than circuit complexity is it's actually much harder to come up with hard examples. So for circuit complexity, we have for P versus NP, we have tons of problems that people have studied, since before any of us were born. And, there's number theoretic problems, SAT, where tons of problems that we think that are conjectured to be hard. In this scenario, it actually took a long time to come up with conjectured hard formulas for strong systems like extended Frege. Yes, this is a quote by Sasha in one of his survey articles. And I mean, one of the problems is that when you you're restricted to write something down that's a propositional formula. So in other words, it's basically, a DNF formula. And so so it seems like what happens is when you write something down that's DNF or that's a propositional formula, it's either not true, so then you're not, then lower bounds are useless, or it's not known to be true or false. So yes, so again, that leaves you a little bit stuck. Or you know that it's true, but then usually when you know it's true, you have some kind of proof that it's, you have a proof that it's a tautology. And usually that proof is formalizable, efficiently, at least in extended Frege. So when you try to come up with explicit families of combinatorial principles that are tautologies that you think require big proofs, it's very hard to come up with them. And also even non-constructively, for circuit lower bounds, it's easy to, with a counting argument, it's easy to show that there's, non-uniform functions that there's way more functions on n variables than there are poly-size circuits computing functions on n variables. And here we can't do that anymore. So you try to count tautologies, we don't know how to, it doesn't seem like the number of tautologies is big enough compared to the size, compared to counting proof size. So we don't even have any way to prove non-constructive bounds. If you want to just, it's a little bit easier to construct examples that we conjecture require super poly-size Frege proofs, or examples that are, if you're going to prove a lower bound for a proof system, then this principle will be, in other words, there's complete tautologies for a proof system. So that's what the soundness is. So soundness, P, is going to be some kind of a propositional formula. It's of this split type. It has an A part and a B part. I mentioned it before, and it's expressing soundness or negation of soundness, because the A part says that we have a P refutation of the formula Z, and the B part saying we also have a satisfying assignment for Z. So if this was true, then the proof system would not be sound. So assuming the proof system sound, this soundness formula is the way I wrote it, the negation of it is unsatisfiable. And it turns out to be complete. So soundness of extended Frege is sort of complete in the sense of if Frege could, and this was something that Cook showed, and it was later showed for more proof systems by Buss, I believe, that if you formulate soundness of extended Frege, if Frege systems can prove soundness of extended Frege with poly-size proofs, then Frege equals extended Frege, and it's an if and only if. But we know that if there's some, if we can separate Frege from extended Frege, that this soundness principle will do that. Similar results for like Frege versus, you can express soundness of Frege, and that's kind of complete for like TC0 Frege versus Frege, and so on. But this is kind of, this soundness principle is a little bit hard to work with because it's not very combinatorial. On the other hand, I will mention the result that I always really liked by Jeremy Avigad from a while ago. And he basically reformulated soundness of extended Frege just in a very nice way that's combinatorial and talking about like hereditarily finite sets. So it's some kind of a nice version of soundness of extended Frege that looks more combinatorial. And I don't think there's been any follow-up work to his paper that's fairly old by now. Okay, so we have these soundness things, but so far they haven't been too useful. And then, like I said before, for like Frege systems, there are some examples. So for example, I think this one was formulated by Cook and Solstice. But you can express like for two n by n matrices A and B, if A times B is the identity matrix, then B times A is the identity matrix. So that's, and let's just say we're in a finite field. So you can express this as a small formula. And how would you prove this? Well, the normal way to prove this is you would want to compute the inverse. And you would need the determinant in order to prove this, because you'd want to, you'd want to take the inverse, basically multiply the left side by A minus 1, and the left and the right side by the inverse of A to eventually get the right-hand side. But to do that, you need to be able to compute the determinant to know that the inverse exists. And that we think requires quasi-polynomial size formulas, not polynomial size formulas. And so for that reason, these matrix identities are believed to require super polynomial size Frege proofs, but they do have poly-size extended Frege proofs. So this is a concrete candidate for giving a super polynomial separation between Frege and extended Frege. And it's just one of many examples. There's some other combinatorial principles that where the only proofs we know of boil down to, being able to compute the inverse of the determinant. And we think those functions are hard for poly-size formulas. Okay. And then the third type of hard formulas is basically random formulas coming from a distribution of formulas where we can prove that most formulas in the distribution are either tautologies or unsat. I'm going to do unsat. It'll make it easier for me. So you have a distribution on formulas, and you can prove with a counting argument that most of the formulas in this, almost all of them, are unsat. And so if you take a random one, you expect it to be unsat. And we have examples of such distributions where we think that a random formula from the distribution should not only should it be unsat with high probability, but it should require a large extended Frege proof even with high probability. So I'm going to describe some of those. The first one, probably all know about it, just random KCNFs above the threshold. So this is one way to pick a distribution of unsat formulas or with very high probability. Almost all of them are unsat. So we're going to pick a random, this is a distribution of KCNF formulas, and we're going to pick sufficiently many clauses, each clause of width K, and we'll pick them all IID, and the number of clauses will be chosen to be above the threshold, meaning the number of clauses N will be delta N, where delta will be chosen to be above the threshold. So what I mean by the threshold is this, red line here shows for K equals 3, that above this line, if we pick a random formula with delta N many clauses, it's with extremely high probability unsatisfiable. And to the left of the red line, we know that with high probability, the formula is satisfiable. Okay. So this is this is a distribution of formulas, and by these results, the threshold properties of these formulas, we know that they're almost certainly unsat above the red line. And these are actually like benchmark formulas and important for all kinds of different reasons. Structural properties of these formulas seem to relate to our understanding in general of SAT algorithms and of proof systems. Again, they're very natural and commonly studied distribution benchmark candidates for satisfiability algorithms. And yeah, I'll skip number 3. And then, in fact, Feige's conjecture is a conjecture that basically is asserting, the strong version of Feige's conjecture is asserting that it's hard to decide for a formula above the threshold. It's hard to decide whether it's unsat or not. In his conjecture, most people believe it, I think, and it's been used to prove some inapproximability results that have not that were not known to be provable under more standard assumptions. And so this is one example that's been well studied, and we know exponential lower bounds for resolution proofs of random formulas above the threshold. And moreover, we even know that when we're way above the threshold, like almost at n squared clauses, like n to the 3/2 clauses, each of, a 3 CNF formula, random one with n to the 3/2 clauses, even with that many clauses, so we're way up here, we're way unsatisfiable. Even there, we know that resolution proofs require exponential size. And actually, even for random formulas, we even have lower bounds for like cutting planes now, which is a recent result. And for some of the semi-algebraic, most of the semi-algebraic systems, SOS, and also unsats. So most of the stuff below the line, with the exception of AC0 Frege, we not only do we have exponential bounds for those proof systems, but we know that random KCNFs are also hard. Okay, so a really nice view is to consider like not just a particular one, but to view, I sort of said this in the beginning, so view this more generally as this is a way to come up with a whole bunch of different hard distributions, and it's called proof complexity generators, and it was defined independently by these two groups. Oops, I need to do that. By these two groups of authors, maybe about 10 years ago. And the idea is that you have you have a function f that's mapping elements from a domain D to to something in this range R, where R is huge compared to D. So think of D as being maybe, I don't know, whatever size D is. Think of R as being super polynomial or exponential in relative to the size of D. So it's much larger. And then the associated formulas will be FV, where V is so for every V in the range here, we have a formula F sub V that's going to state that V is not in the range of this function F. So we want F to be efficiently computable so we can express this efficiently. So we have, think of F as being some polytime function, and F sub V states that V is not in the range of F. And since R is huge compared to D, for almost all V's in R, it can't be in the range, because this is by the pigeonhole principle. That makes sense? So I'll give you some examples to maybe make it more concrete. Oh, let me first say that, and F doesn't even have to be a function. It can be a mapping that maps each element U in the domain to a small, it can be just a graph here where the left degree of all the vertices is very small. So instead of being a function, it maps each element in U to a small subset of R, very small. So think of F as taking U to, say, a very small subset of R. And then the hard is, again, as long as the degree here times D is much, much less than R, the size of R, then most V's here will be outside of the range of F. And so again, the hard distribution is for every V over here, you state F sub V is a formula that states that V is not in the range of F. Okay. So random K-set fits in this framework. The left side is all 2 to the n truth assignments. And I'm going to do K equals 3. So the left side is all 2 to the n truth assignments, and the right side is all 3 CNFs over n variables with m. This should not be n. I think this. Let's do 1 plus epsilon or something. I don't know. This is like, I don't know, maybe 100 n clauses, or I want to be above the threshold. Okay. And then a counting argument shows, that almost all CNFs above this threshold, won't be satisfiable. So this mapping, again, will have the property that the degree here times the size of the domain is much, much less than the size of the range. And the hard distribution is just, you pick a random formula. So F sub V, which states that something is not in the range of F, is just saying that the CNF here is not satisfiable. Make sense? So I'm just explaining how random K-CNFs can be viewed in this more general way. And some other examples is planted clique. So so here I'm going to pick a graph. So on the right-hand side, I'll have like all graphs with, say, half the edges present and half the edges not present. And we know for such graphs that with extremely high probability, the maximum clique has size roughly log n with very high probability. So on the left side, we'll associate with the left side all K subsets of the vertices where K is like n to the epsilon. And we're going to think of a subset as like a planted clique. And the function F will map, if U here is a particular subset of n, it'll map U to all of the graphs where the graph contains a clique on that subset. Okay. And then, so then F sub V, for one of these V's, will just say that, which always says V is not in the range of F, that'll correspond to saying that the graph V has no clique of size n to the epsilon. That make sense? So, and another example is where f, and this is a pretty general example, is where the function f is, we said before we want it to be polynomial time, but let's think of it as a Nissan-Wigderson generator. So it's a particular pseudo-random generator that maps, a string u to a much bigger string v. It's easy to compute in the forward direction, and it's hard to, we think it's hard to compute in the opposite direction. And so now the function fv, the formula fv will say that some v is not in the range of the generator. And a conjecture by Razbrov, and I think Krajcik also, states that any polytime Nissan-Wigderson, for any polytime computable Nissan-Wigderson generator, it's hard on average for NC1, that it's also hard for Frege, and a similar conjecture for extended Frege. That states that any Nissan generator that's computable in the forward direction in NP intersect co-NP, that's hard on average for P/poly should also be, that corresponding F sub V should be hard for extended Frege. Does that make sense? So these conjectures.
Sorry, shouldn't the f be the function itself that is used in a Nissan-Wigderson?
Yeah. Yeah,
Not-
sorry, I'm using, what I mean here is you have a function f, it's easy to compute in the forward direction, hard on average to compute in the other direction. And the conjecture, I'll do this one down here. The conjecture is that when you take a random formula f sub v, which states that v is not in the range of this Nissan-Wigderson generator, so that's a propositional formula. It's usually, well, depending on whether I want to say it's in, let's have the formula say that v is in the range of the generator. So almost always that's going to be unsacked because, because the size of the domain and range are so different. And the conjecture is that for a random f sub v, that's going to be hard for extended Frege because it's going to require super polynomial size Frege proofs, extended Frege proofs.
Right.
And I think that these are really our best examples that we have. And an instance of this thing is where where the function f is actually the function that maps, where the domain here, it corresponds to all circuits of some small size, say size n to the 10. And the right-hand side corresponds to all possible 2 to the n Boolean functions. And the mapping maps the circuit to the corresponding function that it computes. Okay, so this is an example of, you could think of this as an example of a pseudo-random generator, or a function that, that maps small elements in a small domain to elements in exponentially bigger range. It's easy to compute in this direction, and we believe it's very hard to compute in the opposite direction. And the f sub v, what is it stating? It's stating circuit lower bounds. So it's stating v is not in the range of f. In other words, it's stating that this function v here is not computed by any circuit of size n to the 10. Okay, so when we instantiate f to be, a mapping from circuits of small size to Boolean functions, this is an instantiation of this general idea, and then the f sub v's are stating circuit bounds.
These are functions on log n variables.
Sorry?
You're thinking of these as functions on log n variables.
Well, so.
Like, why do you have only 2 to the n Boolean functions?
Oh, that's a mistake. No wonder. Yeah, sorry. I'm very sorry about that. Yeah. Yeah, so sorry. The strings have length. The length of the v's is 2 to the n, and the length of the u's on the left is something more like n to the 10. Thank you. And expressing this is a little bit tricky because you have to say that so the number of variables to express this thing. So v is some particular function, right? And the variables of f sub v are the variables that describe the circuit. So there's like roughly polynomial in n many variables. But to express this, you have to, and propositionally, you have to say, that the function v is not computed by the circuit. So you have to kind of run over all 2 to the n assignments and say that, one of them makes a mistake. So the size of this propositional formula f sub v is going to be like on the order of 2 to the n. That's going to be like, it's going to be big, 2 to the n. But the obvious brute force proof is to, run over all possible values for the variables. So that would be 2 to the n to the 10 in this case. And so that would be super polynomial in the size of the input. You can already see that this is kind of connected to natural proofs because, in an intuitive sense, because how are you going to avoid a brute force search over all circuits of size n to the 10? Or intuitively, you have to kind of come up with some property that such circuits have and rule out that property. And that property should be not too difficult to express, because it's hard to express, so the proof will be big. So it has to be like a simple property. Okay. And, just to say why we believe that this should be hard. Well, first of all, we think, we do think that, what am I trying to say here? Let me just, maybe I don't have any justification for why we think this should be hard, but I will say that what's interesting is that in a fairly old paper by Razvarov, he showed that in contrast to the fact that we think this is hard, all the circuit lower bounds that we have so far are actually formalizable in extended Frege. I don't know about the current ones, but all of the ones at the time. And in the process of proving this, he actually came up with this nicer proof of the switching, well, very nice, I shouldn't say nicer, very nice proof of the switching lemma that was, because in order to show that the proof was formalizable in extended Frege, he needed to actually change the proof and come up with this. And that new proof was like very useful. So just the exercise of formalizing these circuit bounds as small extended Frege proofs. First of all, it wasn't an exercise, it was difficult to do for some proofs. And also by doing that, it shed further light on the circuit lower bounds themselves. Okay, so already here we're talking about, circuit lower bounds is a very natural candidate for hard tautologies for propositional proof systems. And I just want to say a little bit about sort of what do we know and what are people studying in terms of trying to understand the proof, how hard it is to prove circuit lower bounds in say Frege and extended Frege. And so I already said that the existing ones we already know that they're all not hard for extended Frege. So the bounds for the lower bounds for parity for AC0 mod 2, Smolensky, basically almost all the lower bounds that we have, the monotone bounds, they're all easy. And so the question is, how hard is it to prove P equal NP or P not equal NP feasibly? In other words, with an extended Frege proof. So I first just want to talk about, most people don't talk about hardness of proving P equal NP because most people think that P doesn't equal NP. So then of course you can't prove P equals NP, but let's just assume for the moment that P did equal NP and just think for a minute about, well, how hard could we prove that feasibly? And so Cook, a long time ago, I don't know exactly how long ago, but for sure in the 70s, had kind of come up with this working hypothesis that basically all the polytime algorithms that we have so far have feasible correctness proofs. So in other words, if you have an algorithm that solves matching in polynomial time, you have to have a correctness proof that algorithm works. And that correctness proof is always, historically, has always been polynomial time if the algorithm runs in polynomial time. So in other words, historically, or the working hypothesis is you don't ever, or just rare instances of any, of algorithms that are feasible where you have to go way outside of, where you need much more expressive power in the proof system to prove correctness. So if P were to equal NP, but you couldn't prove it feasibly, then it would mean that the algorithm for SAT would have to be extremely unusual, not like the kind of algorithms we're used to. It would have to be non-constructive or somehow just, quite different than the algorithms we're used to. So for that reason, I think proving that P equals NP, if one could prove that you can't prove P equals NP efficiently, I think that's super interesting, even though it doesn't seem to be something that people are currently working on very much. But there is quite a bit more work on trying to show that it's hard to prove P not equal NP. Okay, so that's I've been talking about that already, like trying to prove that it's hard to prove circuit lower bounds in extended Frege. And there's a body of work on this. I would say it starts with Rasbroff-Rudish, who proved, came up with his natural proofs definition. It doesn't correspond to a proof system, but they proved this lovely result that shows that if you could prove this in a natural way, that would break crypto assumptions. And the intuition behind that was this combinatorial property that was relatively easy to express relative to the truth table length. So polynomial in the truth table length, where where that property is distinguishing hard functions from easy functions. And we all know that's closely connected to MCSP and all kinds of other stuff that we are going to talk about in this semester. So I think to me, this is really like the starting point for trying to understand whether or not it's hard to prove P not equal NP feasibly. So then there's a body of work on trying to prove unconditional lower bounds it's actually unconditional lower bounds for the statement that some function in NP does not have poly-size circuits. And that's formalized in the way that we said before. You take some function and you express that it doesn't have a poly-size circuit. And there's some really, these are highly non-trivial papers that show that even though these proof systems are quite weak, so Rasbroff managed to show it for resolution in this paper, and then for a generalization of resolution where the lines are disjunctions of, so instead of being clauses, the lines are disjunctions of conjunctions of size log n. So it's still a pretty weak proof system, but he was able to prove that there's no, that this proof system and this one, they can't prove circuit lower bounds in polynomial size.
Wasn't it Raz the first one who showed it for resolution? This circuit.
Yeah, I put it here because I put it here because I don't remember if well, okay, it matters what the encoding is. Sometimes you need the functional all of these lower, let me just say one thing. Pretty much all of these lower bounds, most of them, they work by reducing to a very weak version of the pigeonhole principle, which states that you can't map like 2 to the n things to, I don't know, polynomial and n, that there's no one-to-one mapping from 2 to the n things to polynomial and n things. So that's how these results, so in order to get to prove these results, you actually have to prove that extremely weak pigeonhole principle is hard for the given proof system, which is why we're stuck with these very low-level proof systems, because when you get a little bit stronger proof system, then it can prove the weak pigeonhole principle. But the workhorse behind all of these is lower bounds. And yeah, you're right. This was the first unconditional resolution lower bound for this super weak pigeonhole principle, mapping like exponentially many things to polynomially many things.
I think Rasborough was showed it first for the polynomial calculus.
Anyways,
So in '98. So Rasborough was the first for PC, and then Raz was for resolution.
yeah, I didn't mention that here because I thought it would be too much, but yeah. So anyways, these results, especially this one, is highly non-trivial. But one weakness of, so I think they're really, I don't understand this result, but one weakness of these results is they're not saying too much about circuit lower bounds at the end of the day, because the way they all work is you want to say, okay, there's no poly-size circuit for SAP. So in particular, that means there's no circuit that's a DNF formula where each term in the DNF is corresponds to a total assignment of the underlying variables. In other words, a DNF formula where each term corresponds to a total assignment to the variables, is really just a list of all of the assignments where the function is 1. Okay, so if you have a function on n variables and it's like, say, 1 half the time, or a good fraction of the time, and 0 a good fraction of the time, then any such DNF of that form will have to be, if I'm forcing you to just look at these really simple circuits that just list all the ones of the function, then obviously the size of that DNF has to be the number of ones of the function, which is exponential if there's half many ones. And so that's the lower bound is actually for those really simple types of circuits. And the argument is just that, if you did have a small DNF of that form, then you would violate the pigeonhole principle. So again, the proofs are really cool, but they're not, in my head, they're not saying too much about why, why SAT is hard. And I want to mention another result. I don't remember how old this is. I don't have the year here, but there's a really nice result. Jan Pick, who proves like what do we call these things?
Escalation.
Rahodi, what's the name of it?
Escalation.
Escalation, thank you. Is it escalation? No, there's another word. Amplification, harness amplification. That's what it is. So he shows that for Frege systems, that if you look at a particular statement, which is a pretty natural statement, that barely superpolynomial lower bounds, for that statement actually gives superpolynomial lower bounds. So indicating, well, first of all, it's a cool result, but secondly, indicating that it's going to be hard to even prove something just barely non-trivial, because already that'll give you superpolynomial lower bounds. And then there's a bunch of work that I don't understand very well. So if you ask me any questions, I'm going to ask Rahul to answer. But these are papers, again, with Jan and Rahul Santanu. I don't know if Jan's here, but you could ask him too. And these results, I'm putting them together because they're kind of similar. The first one gives a conditional lower bounds for this type of statement that says, so instead of expressing P not equal NP, so instead of expressing circuit bounds, the statement is going to express lower bounds for a propositional proof system. So it's saying random tautologies are hard for R proofs, for R is a particular proof system. And what they showed is that this statement, so in other words, proving that R proofs of random formats have to be big, that's hard for any propositional proof system. And that's a conditional result. So it has a crypto assumption. And then in a later paper, they proved an unconditional result, not for propositional systems, but for PV for a similar type of statement. The statement is actually, it's a better statement, but the fact that the lower bounds are for PV make it a somewhat weaker result, because here the lower bound held for any proof system, but the statement was sort of not as maybe natural as the statement down here. And these the tools here are very different than the tools up here. So I think it would be super interesting to somehow find a way to combine the ideas here, which I don't understand, but maybe we can do that this semester. Somehow combine these really interesting ideas with this combinatorial approach. And then the last result that I wanted to mention is there's a result by Rahul and Ido. So I told you before that we know that IPS lower bounds imply VP not equal VNP. So we have this direction. And they proved an implication in the other way that VP not equal VNP kind of implies IPS lower bounds. But there's a caveat because we don't know the statement. That what they show is VP not equal VNP implies IPS lower bounds for a particular statement, but we don't know if that statement is actually a tautology. So it's not totally clear if this is, is vacuous or not. But there's good reason to believe that the statement is a tautology. I guess there's good reasons in both directions, but anyways. Yeah, and this is probably not everything that's been done, but I just wanted to give you some feel for, for what's known. I think there's just a whole lot to do here. And there's huge gaps between these kinds of results that are for quite strong proof systems, very strong proof systems, but the statements of what they're proving, either they're conditional, and or this one is conditional, and a statement is a little bit not natural. But they're proving really interesting, proving results for strong proof systems, whereas these are really weak systems, but it's completely unconditional. Yeah, so this is my kind of last slide, or second to last, maybe, I don't remember. But so I just wanted to show like the web of connections here, since this is meta complexity, how in my head, there's probably even more arrows, but how everything's connected. And I should have put MCSP somewhere in here. But anyways, we can talk about that sometime later. And then I just wanted to mention, there's a lot of good references, because I know this is probably quick, especially if you're new to proof complexity. There's a book by Jan called Proof Complexity. It's a very good, very comprehensive book. There's also some quite a few surveys. I mentioned 3 here. There's another one by Nate Segerland that focuses more on lower bounds. These are maybe more general. And then there's some surveys on algebraic proof systems. Yeah, and that's about all I have, unless you have questions. Yeah, and next up will be Susanna, and yeah, it should be a really good talk.
Okay, thank you, Tony. We have quite a lot of time for questions. Rahul?
I just want to make a comment about the question. So for the you kind of looked at these random CNFs and planted clique as sort of generators, and I mean that's a nice perspective, but those are not proof complexity generators, because some form does the hardness is provable.
Wait, can you say it again? Because maybe I don't think I know what the word proof complexity generator means. So maybe you should clarify that for the audience and me.
For every string in the codomain, that you can't show that it's not in the range. So if you have a mapping from like n bits to m bits, where m is greater than n, for every string y of length m, you can't show that y is not in the range.
Oh, I see. So you're saying for the strong proof complexity generators, the conjecture is that for everyone it's hard.
Yeah.
But you're right, because I just care about whether there is one that's hard.
Yeah.
But you're right, there is a difference. For Nissan Vigorson, I think people think everyone is hard. And you're right, for random ones, it's, yeah, should be clear that there's some really easy ones.
But yeah, the distinction is just interesting. If for random ones, we believe it to be hard, but for other generators, we believe that.
Yeah, interesting. Yep. So, yeah, that's interesting. I guess clique is also playing a clique. I guess anything besides Nissan Vigorson or the circuit lower bound is a case of that, I guess. Yeah, good point.
Any other question?
Michael, if the lower bounds for proving P not in P poly mostly rely on counting principles, could you even say that these weak systems can't do like Shannon counting?
Sorry, could you say it one more time? I had trouble hearing.
Sorry.
So if the weak proof systems that can't show NP not equals P poly mostly can't show that because of counting principles, can we also say that they can't even prove Shannon's lower bounds, like the non-constructive circuit lower bounds, or is there some gap there?
I'm trying to figure out how one would formulate that. We have to formulate that propositionally.
Yeah, I think you formalize it. If the mapping is what you showed.
I think you've showed some mapping which seems quite similar to Shannon, just counting.
No, I'm just saying I think you have to express is a function on n bits that doesn't have small circuits.
Its argument is literally just divisional. I think it does apply to what you just said. Okay.
Somebody
I
said,
didn't.
Oliver said that it is basically the same.
Well, yeah,
I think you've
well, I
shown-
was just the way you would naturally state what is Shannon's
proof or whatever. It's just the pigeonhole principle applied to that specific generator that takes circuits to their truth tables.
Yeah.
From my understanding, what Tony said is we have a lower bound against proving it for that specific function.
So basically you said that you already showed this in one of your slides, that the mapping from circuits, small circuits into the 100 to the set of all Boolean functions, you said it is hard. So it's, I think that's what Marco asked about.
I'm not sure I'm following this because I'm having trouble hearing, but in my head, like it's easy to formalize this in S12 or something like that. And there, I think it's probably true, but I don't know how to make sense out of it propositionally at the moment, but maybe I'm missing something. Does that jive with what you think, Oliver?
Yeah.
Okay, so there's no other questions. So yeah, it was really a fascinating talk and fascinating questions. Thank Tony again.
See you in a week or 2 weeks.